In this video, I'm going to show you what are the power series and how we can find the radius of convergence and the interval of convergence of these series. A power series is a series in this form: sigma n from usually 0 to infinity c sub n x to the power of n. In this formula, x is the variable and the cn's are constants, which we call them the coefficients of the power series. If you put 0 for n, the first term of the power series is c sub 0. If you put 1 for n, the second term is c sub x to the power of 1. If you put 2 for n, we get c sub 2 x to the 2, c sub 3 x to the power of 3, and so on. Note that a power series may converge for some values of x and diverge for other values of x. For example, this is a power series, sigma n from 0 to the infinity x to the power of n over 2 to the power of n. For example, if we put x equal to 1 in this power series, we get to this series, sigma n from 0 to the infinity of 1 to the n, x is 1, 1 to the n over 2 to the n. 1 to any power is 1, so we can write this in the form of sigma n from 0 to the infinity of 1 over 2 to the power of n. This series is a geometric series, which ratio of that is 1 over 2. And we know that in geometric series, when the ratio is less than 1, the geometric series is a convergent series. So for x equal 1, the power series is a convergent series. But for example, if we put x equals 3 in this power series, we get to sigma n from 0 to the infinity 3 to the power of n over 2 to the power of n, which we can rewrite this in the form of sigma n from 0 to the infinity of 3 over 2 all to the power of n. This is again a geometric series with the ratio 3 over 2. Because the ratio of this geometric series is greater than 1, this geometric series is divergent. So as you can see in this example, some values of x make the power series convergent, while other values make the power series divergent. In this video, we want to learn how we can find the values of x that make the power series convergent. More generally, a power series is in the form of sigma n from 0 to the infinity c sub n times by x minus a to the power of n. If you put n 0, the first term of this power series would be c sub 0 times x minus a to the power of 0. We know that anything except 0 to the power of 0 is 1. So if we put n 0, the first term of this power series is c sub 0. If we put n 1, the second term of this power series is c sub 1 times x minus a. This third term is c sub 2 times x minus a to the 2, and so on. This general form of a power series is called a power series in terms of x minus a. Because in the terms of these power series, we have x minus a. We call them the power series in terms of x minus a. Or a power series centered at a. Or a power series about a. Note that if in this general form we put a 0, this general form will become c sub n times x minus a, because a is 0 will be x to the n. And if you compare this with this form, you can see that this power series that we had here is a power series whose center is at 0, or a power series about 0. So when you have a power series, you have to be able to immediately find the center of the power series. For example, when we have a power series in the form of x plus 2 to the n over n factorial, this is a power series whose center is at negative 2. To find this negative 2, you have to set actually the expression inside of the bracket equals 0, and x would be negative 2. For example, if you have a power series in the form of x minus 4 to the n over n squared plus 4, if we set x minus 4 equals 0, x would be 4. And so this is a power series with the center 4. Now let's back to our question. How we can find the values of x that make a power series convergent? For finding the values of x that make a power series convergent, we can use the ratio test or the root test. Consider this power series sigma n from 0 to the infinity x minus 1 to the power of n over 3 to the power of n. We want to find for what values of x this power series converges. To answer this question, we use the ratio test. First, I name the expression in front of the sigma a sub n. So I suppose a sub n to be x minus 1 to the power of n over 3 to the power of n. Based on the ratio test, a series in general is convergent if this limit is less than 1. When a sub n is x minus 1 to the power of n over 3 to the n, a sub n plus 1 is x minus 1 to the power of n plus 1 over 3 to the power of n plus 1. For finding a sub n plus 1, we have to replace every n in a sub n. We have to replace every n with n plus 1. So for finding a sub n plus 1, you have to replace every n in a sub n with n plus 1. Now let us start to find the limit. Limit n approaches infinity. A sub n plus 1 in numerator, so x minus 1 to the power of n plus 1 over 3 to the power of n plus 1, all over x minus 1 to the power of n over 3 to the power of n. Now note that we can write the expression inside of the absolute in the form of x minus 1 to the power of n plus 1 over 3 to the power of n plus 1 times by reciprocal of the expression in the denominator. And reciprocal of x minus 1 to the power of n over 3 to the n is 3 to the power of n over x minus 1 to the power of n. Now let me show you how we can simplify this expression inside of the absolute. In the absolute, we have x minus 1 to the power of n plus 1 over 3 to the power of n plus 1 times by 3 to the n over x minus 1 to the n. Note that x minus 1 to the power of n plus 1 is actually x minus 1 to the power of n times x minus 1. And 3 to the power of n plus 1 is 3 to the power of n times by 3. And the second fraction is 3 to the n times x minus 1 to the n. Now if you look at the numerator and denominators, we can see that we can cancel this 3 to the n with the 3 to the n, and x minus 1 to the n in denominator cancels with this x minus 1 in the numerator. What remains is x minus 1 over 3. So the expression in the absolute is actually x minus 1 over 3. So this limit equals limit n approaches infinity of absolute of x minus 1 over 3. Now note that in this limit n approaches infinity, but here in the expression we don't have any n, and so this limit equals to absolute of x minus 1 over 3. By the ratio test, we know that the series converges if the limit, which in this case is absolute of x minus 1 over 3, is less than 1. So by solving this inequality, we can find for what values of x the series converges. Because 3 is positive, we can pull out 3 from the absolute, and we can write this in the form of absolute of x minus 1 over 3 less than 1. If we multiply both sides of this relation by 3, we get to this expression, absolute of x minus 1 less than 3. This 3 here is radius of convergence for this series. In general, if we use ratio test and we get to a relation in the form of absolute of x minus a less than a number, say r, this r is radius of convergence of that series. Because in this case, we get to this relation, 3 is radius of convergence for this series. Now let's continue solving our question. When absolute of x minus 1 is less than 3, we can rewrite this inequality in the form of x minus 1 between negative 3 and 3. If we add 1 to the both sides of this inequality, we get to this. X is between negative 3 plus 1 is negative 2, and 3 plus 1 is 4. So the series is convergent for all values of x that are between negative 2 and 4. And this is the interval of the convergence of this series. Note that when we are finding the interval of convergence for a power series based on the ratio test, we have to test the endpoints of the interval. It is possible that the power series be convergent at the endpoints of this interval. In this example, we have to test separately for the convergence or divergence of the series at -2 and 4. Let us start with x equals 4. If we put x equals 4 in our power series, we get to this sigma n from 0 to the infinity 4 minus 1 to the power of n over 3 to the power of n. 4 minus 1 is 3. 3 to the n over 3 to the n is 1. So this simplifies to sigma n from 0 to the infinity of 1. It is obvious that this series is divergent. The sigma n from 0 to infinity of 1 is divergent. First of all, note that this series doesn't pass the divergence test. Let me remind you the divergence test for series. If you have a series in the form of sigma n from 0, 1 or any other number to infinity of a sub n, if limit of a sub n as n approaches infinity does not equal 0 or does not exist, then the series is divergent. For this series, a sub n is 1 and limit of 1 as n approaches infinity is 1 and does not equal 0. So this series is divergent based on the divergence test. Another reason that it is obvious that this series is divergent, if we write a few terms of this series, the first term is 1, second term is 1, third term is 1, and so on. And if we add 1 forever, the sum approaches infinity. So the series is divergent. So the power series is not convergent at 4. What about the other endpoint, -2? If we plug in -2 for x, we get to this series, sigma n from 0 to infinity, -2 minus 1 to the power of n over 3 to the power of n. -2 minus 1 is -3 to the power of n over 3 to the power of n, n from 0 to infinity. We can rewrite this in the form of -3 over 3 all to the n, n from 0 to infinity. -3 over 3 is -1, so we get to this series, sigma -1 to the n, n from 0 to infinity. Again, based on the divergence test, this series is divergent. Note that limit of -1 to the n as n approaches infinity does not exist, because -1 to the n alternatively becomes -1, 1, -1, 1, and so on. And so this limit does not exist. It doesn't approach to any specific value. And because this limit does not exist, based on the divergence test, the series is divergent. So at the other endpoint also, the series is divergent. So let's conclude what we found about this series. This given power series is only convergent at the open interval -2 to 4. And for any other value outside of this interval, the power series is divergent. If we want to show the interval of convergence of this power series on a number line, it will be something like this. let me draw a number line here. If we suppose to 0 be here, 1, 2, 3, 4, 5, -1, -2, and so on, this power series is convergent from -2 to 4, and it is divergent outside of this open interval. And note that the center of this power series is at 1. And as you can see, the interval of convergent is symmetric with respect to the point 1. That's the reason that when we write a power series in this form, we are saying the power series is about x equals 1. Now let's try another example. Sigma n from 0 to infinity, x to the power of n over n factorial. We want to find for what values of x does this power series converges. First, let's name the expression in front of the sigma to be a sub n. So we suppose x to the n over n factorial to be a sub n. And so a sub n plus 1 is x to the power of n plus 1 over n plus 1 factorial. Again, we use the ratio test for finding the values of x that make this series convergent. We have to find limit n approaches infinity of absolute of a sub n plus 1 over a sub n. This limit equals to a sub n plus 1 is x to the power of n plus 1 over n plus 1 factorial over x to the power of n over n factorial. And we can rewrite this in the form of limit n approaches infinity absolute of x to the n plus 1 over n plus 1 factorial times by reciprocal of denominator, reciprocal of x to the n over n factorial. Reciprocal of x to the n over n factorial is n factorial over x to the n. Let me show you how we can simplify the expression inside of the absolute. The expression inside of the absolute is x to the n plus 1, which we can write it as x to the n times x. And based on the definition of factorial, we can write n plus 1 factorial as n plus 1 times n factorial times by n factorial over x to the n. Now if you look at the top and the bottom, x to the n and x to the n cancels, n factorial and n factorial cancels. And so what remains is x in numerator and n plus 1 in denominator. So the expression inside of the absolute is actually x over n plus 1. So this limit is limit n approaches infinity of absolute of x over n plus 1. Note that in this limit n approaches infinity, and so x is a fixed number, is a constant, but the denominator approaches infinity because n goes to infinity, and a number over infinity is 0. So this limit equals 0. Because this limit is 0 and 0 is less than 1, so from the ratio test we can conclude that this given power series is convergent for all values of x, which means that the interval of convergence for this power series is from negative infinity to positive infinity. And in this case, we say the radius of convergence of the power series is infinity. So let's summarize what we learned from this example. If we use the ratio test for any power series, not this particular example, for any power series, if we use the ratio test and the limit of the ratio test equals 0, then that power series is convergent for all values of x. The interval of the convergence for that power series is from negative infinity to positive infinity. And the radius of convergence for that power series is infinity. Now look at this example. Sigma n from 1 to infinity n factorial x to the power of n. This power series is given and we are asked to find for what values of x this power series converges. First, we name the expression in front of the power series a sub n. So we suppose n factorial times x to the power of n to be a sub n. We use the ratio test. Limit n approaches infinity, absolute of a sub n plus 1 over a sub n. This limit equals to limit n approaches infinity, n plus 1 factorial x to the n plus 1 all over n factorial times x to the n. Let's simplify the expression inside of the absolute. Limit n approaches infinity, n plus 1 factorial is n plus 1 times n factorial, and x to the n plus 1 is x to the power of n times x over n factorial times x to the n. We can cancel n factorial with n factorial and x to the n with x to the n. And so we get to this. Limit n approaches infinity, n plus 1 times by x. And we can write this limit in the form of limit n approaches infinity of absolute of n plus 1 times absolute of x. In this limit, n approaches infinity, and so n plus 1, this expression, goes to infinity, and infinity times absolute of x is infinity. So it seems that this limit is always infinity. But this is true only for x when x is not equal to 0. If x is 0, this limit equals to 0. Note that when x is 0, 0 times n plus 1 is 0, and so the limit is 0. So the only way that it is possible that this limit is less than 1 is when x equals 0. From this calculation, we can conclude about this power series that it is convergent only at a single point, and that single point is x equals 0. And for other values of x, the power series is divergent. And we say the radius of convergence for this power series is 0, because it is only convergent for one single point. And so radius of convergence is 0.